and welcome again, everyone. Thank you so much for joining us for today's webinar. It's hosted by the LIMS Forum. My name is Dinah Ramirez, and I'm your moderator for today. Today's webinar, A Guide for Laboratory System Management, is part 6 of a webinar series that's been presented by Joe Liskowski. Today, we'll be focusing on instrument data systems. While you take some time to introduce yourself in the chat, let's introduce our speaker today. If you're joining us for the first time in the series, Joe is an experienced laboratory automation and computing professional with over 40 years experience in the field, including the design and development of automation systems, LIMS, robotics and data interchange standards, and consults on the use of computing in lab work. He currently works with companies to establish planning programs for lab systems, develop effective support groups, and helps people with the application of automation and information technologies in research and quality control environments. So we're excited to have Joe with us here again for part 6 in his series. So let's check in with Joe and we'll go ahead and get started. The floor is yours.
All right, thanks, and welcome to the 6th session in this series. We'll be looking at instrument data systems as part of our discussion of laboratory informatics. This will include the roles and education of laboratory personnel and IT support. As we've noted in these webinars, this companion book will provide useful background information on the technologies, support, and other factors that can impact your ability to effectively use these systems. It should prove to be a useful reference as the webinars get into more technical details. Much of the material in this session is expanded on in Chapter 1 of the book. In this session, we're moving into the scientific aspects of laboratory work, with a review of instrument data systems, their role, and how they impact planning for an effective laboratory computing architecture. In particular, we'll be looking at the silo problem, where laboratory data and information can become scattered among systems, and some methods for relieving the situation. As we have in the previous sessions, we will spend some time looking at the educational requirements for these systems that have widespread use. During the previous session, we covered a lot of ground around the lab system support issue. One point that was noted earlier in that webinar is that much of what has been covered so far doesn't require much education beyond a high level of competence in computer systems and an understanding of modern database technologies to support lab operations. That's going to change in this presentation as we move towards the generation of laboratory data and information through instrument data systems and sample preparation. This is where the weight of science and scientific work will be felt. As you can see in the diagram, we're moving against the flow of data and information, beginning where it was stored and managed, and heading to its origins. We're going to continue the discussion in what would be classically viewed as the instrument lab, where measurements are taken and processed either automatically or manually. When we look at robotics, the line between sample preparation in the wet lab and the instrument systems will begin to blur. But for the moment, we'll treat them as distinctly separate stages. Why is this important to you? The connection between the instrument output and the input to the computer systems represents an important transition. That from physically working with the samples to working with measurements made on those samples in digital form. We no longer interact directly with the data, but let a computer system process it. Everything that is derived from the resulting information is based on the assumption that the processing is done properly. All the work that goes into preparing samples for analysis can be wasted if that assumption isn't tested and replaced with a proven determination. My point in this next session is not to tell you that your data and its processing are wrong, but rather that if you don't do your due diligence, you don't know if it's right. And by right, I mean that it's an accurate representation of the instrument's output and the sample characteristics you're measuring. Once upon a time, instrument output was recorded on chart paper and by visually reading gauges and needle movements. That was the norm. People, you and I, converted ink traces on paper to something meaningful. something that could be used to advance the analysis. We were the conversion tool that translated analog instrument output into data points. That was more easily demonstrated when we watched the needle swing on a meter, projected its position onto a scale, and read a pH value. The same thing happens on some thermometers and automobile speedometers. In modern instrument data systems, the analog signal produced by the instrument might still go to a chart recorder, but more commonly, it's directed to a computer system. The analog signal is converted to one or more digital values using an analog to digital converter, then processed and finally reported, stored, and shared over a network. As we'll see in the next few slides, it's possible to distort the appearance of the instrument data by using settings that are not suitable for the analysis that's taking place. Whenever possible, the converted data should be, at least during the method and instrument qualification validation process, compared against the original analog instrument output to ensure that the converted data is a faithful representation of the instrument-generated signal. As instrumentation develops, seeing the actual analog signal will become difficult, if not impossible. Instruments are available that have no way of connecting to a strip chart, and developing the techniques such as chip-based FTIR and others don't provide access to analog data. It is the responsibility of the analyst, both at the time of purchase and in routine use, to ensure that there are facilities available to allow them to review the instrument output for anomalies. As we increasingly rely on computers as a means of viewing instrument output, we have to ensure that we're not being misled by data filters. There are significant differences between the incoming analog signal and the digitized representation. The analog signal is continuous over time and always present. The digitized version is a series of snapshots of the signal and is represented by a series of individual data points measured at precisely repeated time intervals. The experimenter's job is to choose a set of controls that allow the digital signal to faithfully represent the incoming voltages. If either the sampling rate or the resolution of the sampling is inappropriate and demonstrated properly, the incoming data will be a distorted representation of the signal, and any subsequent use will lead to erroneous results. The images on the screen are examples of analog recordings. Note that on the peaks, the shapes of the curves are fairly smooth. The EEG in the lower left does show some noise that is typical of that type of recording. Most analog charts will show smooth traces, unless the incoming signal has noise that hasn't been filtered out, or if the rapid pen movement is actually part of the data. Stair-stepping in graphics displays of instrument data is typical of digitized analog signals. It's evidence that the incoming signal is only periodically sampled. The effect of digitizing the input is shown in this illustration of an audio signal. The faster the sample rate, the better the fit to the original signal. The slower the sampling, the more distortion. The impact this can have on your data is that if the sampling rate isn't fast enough to adequately represent the instrument output, small peaks can be missed and larger ones can be misrepresented, with errors in the subsequent analysis. Analog to digital data conversion is just the first step in the overall instrument data system model that is typical of instruments connected to separate computer systems. The same model for instrument data systems holds for devices such as pH meters and balances. Inside the device packaging, you'll find the sensors, computing, display, and communications ports. Basically, if we can summarize the instrument workflow model, it looks like something like this. It can apply to a balance, a pH meter, a mass spectrometer, or other device. Now that we've defined the difference between the instrument and the role of the computer system, we're going to look at what happens in the computer in more detail. This is important because this is where all the work that goes into experiments and procedures is described in terms of data and information. If that analysis isn't done properly, then all the work in planning and method execution leading up to it is wasted. The next section of this presentation is going to look at that process in more detail. If we expand that process step within the computer, we'll see the steps shown on the screen. I'll give you a moment to review them. The first step is a conversion of the analog signal to a series of data points, illustrated here by the dotted line. If we were to display those points graphically, that's what we'd see instead of the smooth curve that's produced by the instrument's analog output. Connecting the dots would give you the typical stair-step display. The second step is to measure the instrument output in an intermediate stage of information. In this case, the amplitude of the peak is expressed either as its height or the area depending on the analysis, as well as the retention time in a chromatograph. The third step is a result of the analysis calculated by comparing the measured peak size to a calibration curve that would give us an analysis result that we're looking for. Granted, this is really simplified, but it illustrates the process. These steps are guided by user-controlled parameters and settings. The data systems will come from the vendor with supplied default settings, but those are just a starting point for the analyst to adjust as needed. We can't simply assume that those settings are appropriate for all work. They need to be evaluated and modified to meet your requirements. Instrument data systems provide three sets of elements as a result of processing. In packaged products such as pH meters and electronic balances, only the final result may be available to the user. When available, all three are important since they provide a means of recalculating or proving the final result and answering questions should challenges to the analysis arise. Those three elements can be grouped into two categories: data and information. In these discussions, we've avoided using them as interchangeable terms. In scientific work, they aren't. Data refers to values that have no inherent meaning. For example, the 15th value in a digitized chromatogram or spectra by itself is meaningless. It gains some usefulness when it's included along with other data points. Until then, we can't tell if it's part of a peak, a valley, or a baseline. Information has real meaning. Descriptive measurements for peaks are useful information. The peak at 2.9 minutes is a certain size. That information can be used for a higher order analysis. These distinctions become important when we look at the last stage of instrument processing: reporting, storage, and sharing. Part of the lab's responsibility is deciding how to manage those elements within the information architecture. We have three elements in several places to use them. So how do you distribute the elements into the boxes is up to you and how you want your lab to operate. I'd recommend you make sure that all the elements are available. You'll never know what questions may come up or what you're going to need to answer them. Again, where they go is your decision. There are some points that should be taken into consideration, and that is the next section in our discussion. Before we do that, let's summarize where we are. So far, we've looked at how voltages from the real-world instrument output are captured as digital data in a computer system, described a model of how the process of sample preparation through the comparison of results occurs, and its application to packaged devices such as balances and pH meters, and also looked at the conceptual difference between data and information in laboratory work. The next step in our work is to look at how data and information are managed, the options available to you, and the ramifications of those choices. The goal is to help you prepare for the design of a computing architecture that meets your lab and organization's needs. Our discussion so far have covered the area outlined in red. There are some informatics architectural points to be considered for instrument data systems, specifically the number of instruments supported by each computer system. There are two options: one computer supporting several instruments at the same time, or each instrument having a dedicated computer system. Your choices depend upon two factors: what the vendor supports and how you want to organize your laboratory. Techniques such as chromatography offer a choice of either option due to the low data acquisition rate and processing requirements. Other instrument data systems such as mass spec, nuclear magnetic resonance, and hyphenated techniques require dedicated systems to provide real-time control, data acquisition, and processing. As computing power increases, the need for dedicated systems may change. Why does this matter to you? Much of it can be reduced to cost issues, where you have a choice between system architectures. In addition to hardware costs, there are the points noted on the screen. Each computer will require validation, periodic hardware and software upgrades, which means recertifying the equipment that's ready for work, the space on the lab bench along with the wiring, and the initial installation effort. In addition, each system will need backup and archive support. All of this puts a burden on the support organization. A second set of concerns revolve around data and information management. 4 slides ago, we looked at a matrix of data information and where they might be stored. If you had an 8 chromatograph computer systems and wanted to take a look at the results for a specific sample, where would you start to look for it? Would you have to examine all the data systems? Would you have the data and information in a scientific data management system? Or would you put the information in a LIMS or ELN and the instrument data in one of the chromatographic data systems? Life would be a lot easier if all the instruments for the same technique were tied to the same computer, simplifying the data, information, and management issues. In addition, if there are electronic methods and parameter files, there'd only be one place to look for them. One subject that's been discussed in articles and webinars is that of data silos. That is essentially what we've been covering in the last few slides. The problem as it's been presented is that lab data and information is spread among a number of systems. Managing it, including finding and using it, is a major issue. Data silos can frustrate efforts to distribute and share lab work and the ability to apply data analytics. Note that data analytics, a common phrase, is in quotes, as it refers to a class of informatics analysis rather than instrument output. Given the discussion earlier, labs don't want to distribute instrument data, but rather the information resulting from lab work. The reason for the problem's existence is a lack of effective planning. The potential use of lab work needs to be thought through as part of a laboratory informatics architecture. As we can see in the chart on the left, it's precursor 6 slides ago, you have data and information coming from several sources. The goal is to concentrate the top level of the data information structure in a LIMS or ELN, with the supporting material logically placed where it can be used most effectively to either produce new results or answer questions about existing results. That means the development of a hierarchical structure that minimizes duplication and ensures that the systems are subject to backup and archive policies. If you're looking for information or data, where's the most likely place to find it? That location should have pointers to the next level of data. For example, if a result is stored in a LIMS or ELN, that same record should have a pointer to an SDMS or IDS location, IDS being Instrument Data System, that has the material needed to support that result. One major consideration in determining the distribution of data information among systems is your ability to work with it. If data is moved from an instrument data system to an SDMS, for example, can it be sent back for reanalysis? Some vendors, with good reason, prevent data from being brought back into an instrument data system for further work. The problem is maintaining a chain of custody over the data. If a data file is reintroduced into the system, is there a chance that it's been modified? The primary concern is that of data integrity, a concern that would override other considerations. If the SDMS were, for policy reasons, going to be the ultimate storage for all lab data, then you would have duplicate copies in the IDS and the SDMS. If your policies permitted distributed storage, either avoiding an SDMS altogether, or using it for files that don't have a home somewhere else, then people would know where to look for different data types, something that would argue for consolidation of similar techniques into one system. One thing that would be useful across techniques, and it may exist with some vendors, are data viewers for analytical data stored outside an IDS, perhaps on a scientific data management system, for example. A package that would allow people to examine data in detail. This would be different than the chart systems produced in PDFs along with results reports. Those systems, those graphics, are condensed views of data and don't permit zooming in on areas of interest. The layout on the screen shows one possible setup for managing lab data, information, and knowledge captured in documents. The arrangement considers basic LIMS or ELNs without any provision for an internal laboratory execution feature. There may be several instrument data systems, some with only one instrument attached, another with multiple instruments. All data and information, both those resulting from intermediate analysis and completed calculations, would reside in those systems. We'll follow the data and information flow towards the central data systems, which would be a LIMS or ELN. One goal is to minimize the duplication of data and information. Some duplication is going to occur, but we may want to avoid any unnecessary copies of records. The SDMS would hold any data that was not part of another system. The same holds true for information sources. Reports from the instrument data systems would be held here. The reports would be parsed for information that needed to be sent to the centralized systems. Any documents not held within the LIMS or ELN would be stored here as well. The centralized LIMS or ELN would contain the test or experimental results, any pointers to data or information sources that would be needed to back up those results, and information needed to manage the lab's workflows. Those would include test requests, sample location information, basically anything needed to manage the lab workload and processes. Lab execution systems might send any measurements they collect here so that they would be available for finishing an analysis. This is just one possible layout for distributing lab data, information, and procedures and reports. The LIMS or ELN or additional systems might carry accounting or personnel information. While the primary subject of this webinar is the instrument data system, we can't treat it in isolation. The links between it and other systems have to be taken into account so that the flow of data and information is well defined. And as we've noted, all systems need backup support. If our long-term goal is to automate as much of lab work as possible, there are some things we need to be careful of. When we processed instrument output manually, we became intimately involved with it. We knew how baselines were drawn, how amplitudes were measured. We could see any anomalies that were present. Those unexpected elements might show up as distinct peaks or as bumps or deviations in the trailing edge of a peak. Once a deviation from the expected was found, it was up to the analyst to chase it down, repeat the analysis, and identify the problem component. The impact of contaminants is a problem in any experimental procedure. Now that we're trusting the software to do that work, is it up to the job? Are we trusting printouts that might have filtered out problems? That's for you to determine. It's a matter of making sure the equipment meets the need, and that is part of the validation process for laboratory procedures. What roles do people play in planning for the use of instrument data systems? How do lab management, lab personnel, and the support roles through lab automation engineers, as discussed in Webinar 5, contribute to lab technology management and planning? Some aspects of the work are easily located in people's roles. Others are distributed between two or more groups. Naturally, the size of the organization matters. Large companies can afford to have separated roles, Smaller ones may place the burden on a few people. Lab management is responsibility for the overall ability of the lab or laboratories to meet their organization's responsibilities. That includes managing operations within the lab, responsibilities to group the lab may be supporting, and those organizations they may be collaborating with. Among the key assets that the lab works with and produces are knowledge, information, and data. Lab managers are responsible for defining the behavior of lab systems and the goals that should be covered by laboratory implementations. With regard to instrument data systems, that includes the number of instruments tied to computers, where choices exist, and how the lab data and information are spread across data systems, SDMSs and centralized systems, for example. In order to do that, they need a solid understanding of the capabilities of those technologies and how they apply to lab work. Lab personnel, first and foremost, need an understanding of the science that underlies the lab's work and the stages in technology utilization as they move from manual implementations to automated systems. When it comes to instrument data systems, lab personnel should have a solid understanding of the processes that go on in the data systems that they work with, what happens to their data as it's acquired, processed, down to a series of results. They should also be capable of evaluating vendor offerings against the needs of a specific use and how it fits into the overall lab's computing architecture. The ability to provide an initial level of troubleshooting issues, along with automated procedures and equipment used, is another area of the lab personnel's responsibilities. The problem in educating scientists in the use of laboratory systems is nothing new. These references from 2005 and 2011 point to a problem that still exists today. In my own experience in working with lab personnel, they sometimes don't seem to really appreciate what the equipment does or how to use it effectively. When I ask about setting instrument parameters, their eyes often just glaze over. A few undergraduate schools I've visited have some instrumentation, but the education about their use is minimal. Given the emphasis on data integrity today and the problems that have been reported in the reproducibility of laboratory data, this is an area that needs significant attention. Much of what goes on in laboratory systems development is a function of how the vendor sees the laboratory and its needs. Some are responsive to input from the user community. But the real question is, how do you see your lab and its needs? How do you want your world to work? That is a collective input from you and other users that should drive technology development. One possible direction new development could take is the separation of data acquisition from processing. The instrument would have internal data capture capability for a set of samples, say an autosampler tray, for example, package the data into a file, and then send the file to a computer for processing. This could simplify overall lab information architectures and remove the silo issue. It would require the solution to two issues. The first is standardized file formats for data in two tiers. One tier is the structure of the tray with samples and standard information. The second tier is the data for each sample. Work along these lines has been begun several years ago and remains to see if they are successful. The second issue is security and protection against tampering with the data to ensure that data integrity and fraud are prevented. The upside of this would be the potential for the development of data processing systems and algorithms by third parties. Lab automation engineers would assist by providing technical evaluation of the lab's computing architecture and strategy, including a feasibility analysis, a comparison with similar work going on in other organizations to avoid unnecessary duplication, and the vendor's ability to provide long-term support for the lab's needs. The details of that were covered in the last webinar. The introduction of computer systems into laboratory science raises the bar on what it means to be a competent laboratory worker. That's true whether you're talking about management, lab personnel, or support. You can carry out science without computers, but in a competitive environment where productivity and return on investment have become important metrics, computers and automation are part of that reality. What that means is that we have to be well educated in both the science and the tools that are used to conduct that science. It means that we have to prove that the tools we're using work as we need them to and are appropriate for our requirements. And that's where we're going to pick up the discussion for the next webinar, which is currently slated for June 21st. Thank you very much. Are there any questions?
Okay, thank you, Joe. I don't see any questions in regards to your content at this point in time in the chat box, but I would like to remind everyone that you can submit your questions or comments using the chat box on the right-hand side of your screen. While we wait for any questions or comments to come through, we did have a few questions for Joe that came in before the webinar that he'd like to address. So Joe, let's go ahead and go over some of those questions while we wait for any other questions to come in. So how serious is the silo problem?
Actually, it's pretty significant and actually fairly common. I don't know about you, but I've got piles of paper on my desk, and those are silos. You also might wonder if your computer has a folder that says things I'll get to. Those are silos. The stuff is there, you just got to find a way to make sure that people can use it. The real problem is making sure that people have confidence in how your lab works. If you can't find information, then they're going to have problems believing that they have confidence in the results that you produce. If somebody asks you for information and you can provide it very readily, then they're going to have a lot of confidence that your lab is operating properly. The silent problem is increasing as we start dealing with collaborative efforts, working with results that are developed perhaps by contract laboratories or outside services. They have their silos, you have yours, and then the results go off into other people's analysis and use. So it is a significant issue. It's a data architecture problem that requires planning and really thinking things through. And of course, all these systems require backup and archiving.
Okay, great. Thank you for addressing that. And another question that came in was, why can't we just use our IT people to troubleshoot our systems?
Okay, the basic issue is that most IT people don't have the background needed to understand how the systems, and that includes the computers and the instruments, work together. They don't understand the need, for example, for looking at the data to help isolate problems. They'll do routine maintenance on computers. That's within the scope of their work. But multidisciplinary work may not be, and that means dealing with both the computer side, the instrument side, and it may actually extend to the sample processing systems. Both lab personnel and IT support really need to be more educated to be successful in modern laboratory technologies. We'll see that in the next session as well. But one of the things that we need to deal with that popped up in a video I saw yesterday was that we tend to treat science and technology, computer technology in particular, and engineering as different things. We have scientists, we have IT people, we have engineers. When we really need to start integrating those things into our thinking and be able to use all of that stuff in the course of our work.
Okay, thank you for addressing that question as well. Do those working in the lab need to understand the details of the software? That was another question that came in.
Yeah. People don't have to understand what the program is all about. They don't need to be coders. They don't need to try and get into the programmer's head to figure out what they were thinking. But what they really have to do is understand what that programming is trying to accomplish. We touched that on a little bit already. What factors influence the processing of the data? Are there assumptions that can compromise your work? A few years ago in chromatography, peak detection systems, ran into a real serious problem when negative peaks started showing up because the algorithms assumed that they weren't there. Part of the issue, again, is that we're taught these things. We're taught about the science and the systems separately and not as just a normal part of our work. So people need to kind of raise the bar on what their education is and what their understanding of things are. A few years ago, I was in one lab where basically the sample went in one end and numbers came out printed on the other end, and people had no idea what went on in between. That's not a good situation. They really should understand that stuff.
Okay, excellent. Thank you for answering that question as well. We did get a question that came in through the chat box. The question comes in from Carl. He's asking, what kind of architecture can be expected for the future? And will there be platforms connecting instruments?
That is actually up to you, and that's been a problem. Vendors have often asked people, what is it they want to see? What do they want to see happen? I was at one meeting where 3 vendors stood up, talking about their products, and then they got up and said, tell us what you want. We're guessing what you need. We need you to tell us what's going on. As we're getting faster processors, more storage, and faster techniques, we can start to see instrument techniques collapse down to perhaps one computer system per technique. So if you had 4 mass specs, they'd all be tied to the same instrument, all with the common data structures. So those are the things you need to start thinking about. And if you want them, start telling the vendors you want those things. If you look at the history of data acquisition and instrument architectures and instrument data systems, the stuff we're working with, what the architectures, were formulated 20 years ago and haven't changed very much since then. That was the stuff they had. It worked. People are still using it, and nobody's beating on them to change things, to make things work better. But we need to start looking more at 2 areas in particular. One is integrating the same type of technique into one computer system, and the other is something that we need data standards to do, and that is the ability to have third parties look at different ways of analyzing data. Right now, if you bought an NMR, you'd buy the instrument and the computer system, and you'd run the vendor's software because it was all tied together. But would it be nice to have access to different types of processing software so that you could buy one vendor's product and someone else's instrument data handling material? So what's driving it is you. You've got to tell people what you want and how you want your labs to work and what the problems are that need to be solved. And that's going to become more acute as automation comes in and starts really driving things. As human labor is replaced with machine labor, and people spend more time analyzing information and interpreting it, as opposed to just manually carrying out procedures.
Okay. Thank you, Carl, for your question. And Joe, it does look like that addresses his question. It appears that we may be getting another question. While we're waiting for those questions to maybe come through, again, I just want to remind everyone that, again, this webinar was recorded. We will go ahead and post it to the LIMS forum along with the other webinars in this series, which are already viewable on the LIMS forum.
The question that came up is how to handle complex data and instrument interface in a LIMS. Don't is a simple answer. If you look at what we talked about in the first few webinars, LIMS systems there are different implementations of LIMS systems. Some of them are on-premise. Some of them are shared systems. Some of them are cloud systems. The more response the faster response that you need from an instrument system, the closer you want the computer to be to that system. So a LIMS that may be operating in a cloud isn't going to help very much with an instrument that's working in your laboratory when somebody's standing in front of a screen waiting for a response. There's too many variables there. The system, the network may slow down. There may be a break in communications. There may be a power outage that can occur. So you need something that's reliable. A LIMS is really not a good place to deal with complex data. And by complex, I assume you're meaning things like spectral arrays or mass spec information or large data sets. LIMS can deal with a balance input. It can deal with single data point measurements like a pH meter. But if you're dealing with things like any type of automated instrument, particularly hyphenated techniques, you really want to keep those things separate from there and keep things isolated. One problem is if you wind up with things too tightly integrated, when one thing breaks, everything breaks. So you have to separate things to build in some fault tolerance. Imagine you're running a laboratory with a lot of instrumentation. Everything is resolved into one computer system, and somebody decides to do an upgrade on that computer system, and it doesn't work right. And that system is down, which means the entire lab is down. So you really need to do a lot of planning about that sort of thing. LIMS have their role, but complex instrument data is not a good place for them.
Okay, thank you, Joe. Banu, I hope that answers your question. Banu says it's well explained. Wonderful. Okay, good. So I don't know if there are any other questions that are coming in, but and it looks like we've covered all of our questions that came in previously. So Joe, is there anything else that you would want to cover before we go ahead and wrap up for today?
No, just to invite you, well, aside from just inviting you into the next session, which I mentioned is going to be June 21st, there what we're going to be doing is looking at sample preparation, the processes that are involved, the science that's involved a bit, and we're going to take a good long look at how guidelines and regulatory requirements play into that stuff. Process roles, process analysis. Basically, it's going to finish up the procedure that we started off looking at how data is managed, and now we're looking through at how it's generated and how samples are being dealt with. So that session is going to pretty much tie the whole thing up into one ball.
Okay, great, and we're looking forward to that. So thank you so much, Joe, and everyone who attended today. We really appreciate your time and interest in the topic. As a reminder, we'll be sending a follow-up to everyone registered with a link to the recording as well as the slides, and we'll see you next time. So thank you so much again, and thank you, Joe.
Thank you very much.